So the question is, what do you do when direct substitution doesn't work? How do you find the limit? Sometimes direct substitution won't work because there is no limit. Those are cases where you end up with a expression of the form, let's say 5 over 0, or really any number that's not 0 over 0. In those cases, those are obviously undefined terms, and that means the limit does not exist. So you can't find the limit by direct substitution because there is no limit. But there's another case where you end up with a term expression of 0 over 0, which is the indeterminate form, which we all know just means that there's a hole in the graph, not that there's an asymptote. So the function is not defined at that particular x value. However, there is still a limit because the function is approaching a specific value, even though the function is not defined at that value. So in those cases, in order to find the limit, you would need to find an equivalent function that agrees with the function you're trying to find the limit of at all but that point where you end up with a hole in the graph. And the function that you're going to find needs to be defined at that x value. And in that case, there's a theorem. It's been proved. It's also very intuitive that whatever the limit of the function that's defined at that x value is going to be the limit of the other function that's not defined, that's indeterminate at that x value. So we'll just go through a bunch of examples here. For number 1, and the limit as x approaches -1, x squared minus 1 over x plus 1. And over here, if we try direct substitution, you would end up with -1 squared minus 1, which is 0. And -1 plus 1, which is 0 over 0. That's indeterminate. There is a limit, because that's just a hole in the graph. But by using direct substitution, we can't find that limit. We just get 0 over 0. So to find a function that's equivalent to this function at all but that point, we see if we can divide out, let's say, the denominator, and that way we won't end up with 0 over 0. So in this case, we can factor the numerator. It's a difference of squares over x plus 1. This doesn't equal that. But this is equivalent to this, which is equivalent to x minus 1, because these cancel out. And this is equivalent to that at every value besides for x equals -1. Because that's the original function that we're trying to find the limit of is undefined at that point. However, this function is defined at that point. So because of that theorem that we have, limit -1 squared minus 1 x plus 1 is equal to the limit x approaches -1 of the function x minus 1, which, using direct substitution, because there's no issue with that now, is equal to -2. So that's how that works. It's the dividing out technique, when you're able to divide out a factor that makes it, but it's not 0 over 0. To another example here. Limit x approaches -2, 3x squared plus 5x minus 2 all over x plus 2. Again, -2, we plug it in, get 0 on the bottom, plug it in on top. You get 3 times 4 is 12, minus 10 minus 2 is 0, so that would equal 0 over 0. However, this function is equivalent to, so we get 3x times x. If we make this a positive 2, this a -1, And we get that. Again, just factoring. X plus 2, x plus 2. Just cancel out. So this is equivalent to this. At all but the point x equals negative 2. So we have again that the limit of this function is equal to the limit as x approaches negative 2 of this function, which by direct substitution, 3 times negative 2 is negative 6, minus 1 is equal to negative 7. So that's for cases where you can factor out the denominator, get rid of it, and thereby an equivalent function that doesn't have the hole in the graph. Other examples, this would be one where you're going to factor out the denominator. X over x squared minus x, so the limit of that is x approaches 0. Again, if you just plug in the 0 direct substitution, you're going to get 0 over 0, which is a determinant. And so we have again that if we take this function, we can say that is equivalent to and x's cancel out, get 1 over x minus 1, set all but the point x equals 0. And then if we take the limit of that function, which is equivalent to the limit of our original function, as x approaches 0, is equal to 1 over negative 1, which is just negative 1. Okay, we'll do another example like that. Let's do one where you have to do both numerator and the denominator. So we have the limit as x approaches 2, x squared plus 2x minus 8 over x squared minus x minus 2. Again, if we plug into 2, we get 4 plus 4 minus 8 is 0. 4 minus 2 is 0. 0 but 0 is indeterminate. Can't use direct substitution. So, realizing that these can be factored, try to see if we can get an equivalent function. So we have x plus 4 times x minus 2 over x minus 2 times x plus 1. And there you go. X minus 2's cancel out. We have x plus 4 over x plus 1. And if we're taking the limit of that, again, that's at all points besides for 2. Take the limit of that. So x approaches 2. Again, of x plus 4, x plus 1. End up with 2 plus 4 over 2 plus 1, which is 6 over 3, which is 2. That's pretty much it for the dividing out technique. Factor the function you're given to see if you can find an equivalent function that agrees with it at all but one point. And if you can find that function, get its limit, and the original function limit is the same. Here's another technique that comes up. If you have a function of this form, so if you have the limit as x approaches 4, square root of x plus 5 minus 3 all over x minus 4. You plug in 4, direct substitution, you get square root of 9 minus 3, which is 0 over 0. Can't do it that way. So here we're going to multiply by a useful form of 1. So we kind of have to get a little bit creative. And we're going to say if we multiply this, x plus 5 plus 3 over x plus 5 plus 3, and we're hoping we're going to get an equivalent function, because we're just multiplying by 1, that will not yield an indeterminate form. Let's go ahead and do the foiling. X plus 5 minus 9. And you can see that's going to be x minus 4, so we'll leave its denominator this form. And it's going to yield, again, this is going to be x minus 4. So these will cancel out. 1 over root x plus 5 plus 3 equal to the limit as x approaches 4 of our new function, which by direct substitution is equal to square root of 4 plus 5 plus 3, which is equal to 1 over 6. So this is multiplying by the conjugate. If the function allows to do that, to get a equivalent form, it's not indeterminate. There is one more technique called the squeeze theorem to find the limit when you can't find the limit by direct substitution, but we'll save that